good morning again. We will continue on the aspect of derivation of the continuity momentum and the energy equation, the governing equations, by means of another approach where you are completely working with a arbitrary shape control volume which is not fixed to any coordinate system. Okay, and this is a very interesting approach. So here what we do is we consider a control mass, essentially a system. That means you are considering fixed packet of fluid with a given mass and tracking it with respect to time. So if you assume that there is a fixed mass of fluid with a volume v at a time t, and then after some time t plus delta t, you see the volume changes but the mass content is the same. And if you define any property alpha as the property per say unit volume, and this property is supposed to be a function of time. Okay, so this is the traditional Lagrangian approach. So where you just the observer travels along with the frame of reference of moving frame of reference of the packet of fluid. So and then therefore the property changes are all happening over time, right, rather than the Eulerian approach where the observer is stationary, the control volume is stationary, and then the fluid crosses the control volume boundaries and there is a corresponding change of mass flux quantities of this particular property. Okay, so that is a different frame of reference. So this Lagrangian frame of reference can be used to calculate what is the rate of change of this particular property with respect to time. Okay, so now for that we have taken a small differential volume delta v corresponding to this time t and seeing how it evolves over time. Okay, the same differential volume, what happens at time t plus delta t. So if you overlap these two control volumes, essentially you see that this delta v has probably grown to this size, delta v at t plus delta t. Okay, so therefore what we can do is we can calculate the change delta v at t plus delta t minus delta v at t from the velocity vector. Basically if you take this particular differential volume, so this is delta v t and this entire thing is delta v t plus delta t. So this change is basically the volume of this element that I have drawn here. Okay, so therefore this surface is actually sweeping a distance of u vector dotted with the normal. Okay, so that much displacement is happening to that the differential surface element at time t, and it is sweeping that much of distance. So that should be equal to this difference change in the differential volume. Okay, so this is nothing but your u dot n delta t delta s, right. So this is just how we are representing the change in the volume. If you want to calculate from the Eulerian point of view what is the rate of change of this property with respect to time, okay, from the control mass system, so the mass does not change, so you are just tracking this property change with respect to time. So this is a total derivative, okay, just single total derivative. Okay, so that you have to say, suppose you have a particular value of alpha for this differential volume, so you will have different values of alpha for different differential elements, and you have to integrate all of them. Okay, that will give you the total property of that particular control volume. Okay, so and you want to calculate the rate of change of this particular property. Now this can be written as your limit delta t goes to 0, you can split it up into the property at t plus delta t, okay, minus the property at time t. Okay, so these are the two integrals that you see here, and what I am going to do a little bit of mathematical jugglery. I am just adding and subtracting this particular term right here. So this is integral at v of t alpha t plus delta t dv. So I am just subtracting and adding the same term here. So now if you look at this particular term, okay, So this is nothing but you are keeping the integrand the same, okay, and you are changing the volume, okay, v of t plus delta t minus v at t. So essentially that is like you are keeping the integrand same and you are integrating with respect to a change in the differential volume, so which is nothing but this particular term right there, okay. So this can be combined together and we can write this as alpha t plus delta t dv, where your v changes from t plus delta t to the earlier volume at t, okay. So that can be replaced by this particular term right here and this term that you see. So in this case you are keeping the volume fixed, okay. So this volume is at time t and the integrand is changing, okay, from alpha t plus delta t, okay, minus alpha t, okay. So this describes what is happening to the change in the property from time t to t plus delta t for the same control volume, okay. So this is nothing but the Eulerian derivative, okay. Now what you are essentially doing is you are changing the frame of reference from a moving frame to a stationary frame, okay. So left hand side is the moving frame of reference where you are tracking a control mass with a fixed amount of mass and you are tracking the evolution of the property with respect to time. And when you go to a stationary frame of reference, so that should involve partial derivative with respect to time, that is change of property with respect to time for a fixed control volume. So that is you are converting a control mass to a control volume, okay. Plus now once you convert that to a control volume, there should be some flux of this property which is crossing the control volume boundaries, so that should come in terms of this. So we will see how it comes, okay. So in the next step I am just going to replace this particular terms right here, okay. So this will give me d by dt v of t alpha t dv should be equal to limit going to 0, I am saying alpha t plus delta t, and this is nothing but your change in the volume from Vt to Vt plus delta t, and that I am going to replace by u dot n vector into dt ds, alright. So the dt dt cancels there, so this will be u dot n vector ds. So you are converting the volume integral to a surface integral, okay. So this also will be corresponding to the surface at time t, okay. Plus the other term right here is nothing but the rate of change of this property for the same volume with respect to time. So this is the partial derivative integral v of t, this is d alpha by dt into dv, okay. So is it clear?
So why did you take the material derivative on the left hand side?
Because this is for the control mass or the system, which is essentially a closed system, so it does not allow any mass transfer. So essentially the property can change only with respect to time, spatially it cannot change.
Material derivative includes the spatial changes, right?
Yes, but this is with the reference frame where you are moving along with the particle. So if you convert that to a stationary reference frame, that will have the spatial derivative. So that is what essentially the Reynolds transport theorem does. It essentially transforms, it gives you a relationship to transform a control mass to a control volume, okay. So if you know that, I think after that working out for a control mass will be very straightforward, because if you write the energy conservation for control mass, you do not have things like efflux, right, because it is impervious to mass, okay. So it is much easier to write the conservation for a closed system rather than the open system, and all you need to do is the link between the total derivative and the partial derivative. So that you just substitute and then you will bingo, finally you reach the conservation equation we have derived earlier, which is for a control volume, okay. So very shortly we will see that, but this is just a routine way of substituting. We are looking at two terms here. One, we are fixing the integrand and changing the volume. Okay, so that is being substituted by this particular term here. Okay, and the other, we are basically fixing the volume v of t and trying to track the change with respect to time. So that is the partial derivative with respect to time. Okay, so now we can apply Gauss divergence theorem. You all know that the surface integral can be converted to a volume integral. Okay, so how this can be done? So this can be integrated over volume, then if I apply Gauss divergence theorem to this, divergence of this particular term, that is del dot, okay, you have your alpha, then u vector and integrated over the volume. Okay, so therefore I am just going to replace these terms in terms of the divergence operator, and this becomes d by dt of v alpha dv should be equal to integral. So the entire right hand side is having a common integral with respect to volume t, so this can be d alpha by dt plus del dot alpha u vector, and this is all integrated over the differential volume dv. Okay, so this essentially is the Reynolds transport theorem. I will call this as 1. Okay, so this is the Reynolds transport theorem, which says that you are converting some property variation from a control mass, which is a closed system, to a control volume, which is an open system. So it is nothing but you are converting a total derivative, writing a total derivative in terms of partial derivatives. Okay, with respect to control mass, it is only a function of time, therefore it is one derivative, single derivative, and with respect to the control volume, you have property which is varying with respect to time and space, therefore you have partial derivatives. So as simple as that. Okay, so this can also be written in a tensor notation. Okay, so this is general notation also in tensor form. I think many of you have learnt tensors in your incompressible flows. So I am just going to use some notation here. So the left hand side term stays the same, alpha dv should be equal to d alpha by dt plus d by dx. So I am going to use the subscript k to denote the divergence here. Okay, so this should be again alpha u k. Okay, in fact I can remove the vector, so this itself means dv. Okay, so this is in a tensor representation. Okay, so this here right here means that you are basically going k is equal to 1 2 3 and you are summing it up. I hope all of you can remember your tensor notations. Okay, k equal to 1 becomes dx. Okay, similarly here du by dx, k equal to 2 becomes this dv by dy. So you can keep changing this particular thing with respect to whatever. Suppose you write your x momentum, so you can write your momentum in the x direction and keep this as 1, and we will see what is this alpha there. Similarly in the terms of energy, so you have to define alpha and then the index also will keep changing accordingly. Okay, so this is your theorem. We will apply this to derive the conservation principle. Number 1, conservation of mass. Okay, so when you talk about conservation of mass, so what should be your property alpha be? Alpha, we are defining property per unit volume. So if you conservation of mass, so this is mass per unit volume, right? So your alpha should be rho. So simply replace your alpha by rho. So what it essentially states, what your conservation of mass says, if you have a closed system, there is no mass entering and mass leaving because this is a closed system. So that is the advantage of using Reynolds transport theorem. You don't have to consider any flux of mass. Okay, so all you are bothered about is this total derivative. So what it says, your d by dt integral over v, your rho dv should be, this is the mass, the total mass 0, right? Because as I said, this is a control mass, so the mass cannot change with time. Okay, so this is 0. So now what you know is this is the fundamental starting point for a closed system. So now you also know from the Reynolds transport theorem the link between the total derivative and the partial derivative. Okay, so now you can write from a control mass to a control volume the same expression. Okay, so that will say that this is equal to v of t, okay, d rho by dt plus del dot rho u dv equal to what? 0 from the Reynolds transport theorem. Okay, so now for this condition to be valid, the integrand has to be 0, correct? So therefore this gives you your continuity equation. Okay, so in a coordinate free representation. So momentum, I think you can do it yourself. You have to just apply the Newtonian law. Okay, for start with the closed system, apply the Newton's second law for the closed system, and then you can link the total derivative with respect to the partial derivatives. Okay, so I am going to do that for energy equation. So you can probably apply the same principle for the momentum equation also. Okay, now what I am going to do is, for this particular case, I am going to consider the corresponding transport or maybe the different forms of energy which are acting on this control volume, right? So one component which I will combine together, the body force and the viscous forces together, I will say that they are acting in some direction. Okay, let me call this as some p vector. Okay, this does not mean pressure here, it has all the components of viscous and pressure and body, viscous, body and pressure forces. Okay, in one single component I am showing all these subcomponents are included under that p vector. Okay, so naturally what will be the work? If you have a p vector acting on this differential volume and you have velocity vector in this direction, so the work will be p dot u vector. Okay, so the corresponding displacement, that is along this particular velocity vector direction, should give me the work. Okay, so apart from that I can also have heat transfer. Okay, and I can just say I have some heat transfer like this q vector. Okay, so now I cannot do this in any coordinate system, it is arbitrary in any direction. So I am just using the vector notation and I am going to substitute there. Okay, so this is your heat transfer rate. Okay, in fact I can use the heat flux here, right here. So, okay, q double prime vector heat flux. Okay, so you have some internal energy for this particular system. You have this is a control mass. So essentially what is happening, you are not considering any flux of energy. Okay, it is close to mass, but it allows work and energy transfer to happen. Therefore you are considering the component of work, that is p dotted with u vector and heat transfer. So now we can write the first law of thermodynamics for a closed system. Okay, now first we will define what is alpha here. You have to tell me property alpha for when you consider energy. So you have components of internal energy and kinetic energy, right, per unit volume. Okay, so you have U plus U square. Okay, in fact I can write this as some magnitude of U vector square. Okay, so I am just expanding it in the conventional Cartesian coordinate system, okay, just for your convenience. And so what else? Is this correct? This is per unit mass, okay, but I need property per unit volume. Divide by density, multiply by density, right? That's it. Okay, so this is my alpha. Now I will write the conservation for energy to this particular closed system, and that should give me what? D by dt. I can integrate this alpha, that is rho into, so in fact I am going to use a coordinate free representation here. So I will write this as half of U vector dotted with U vector, right? That is the same, U square plus V square plus W square if you write it in a Cartesian coordinate system. So I am just going to write this as plus U plus half U dotted with U dV. This is my left hand side term for a control mass. I am writing the first law of thermodynamics. So that should be equal to the work, okay, and the contribution of work and heat. Okay, only this can contribute to the change of energy of this particular system. I am now going to split into two components. So I am saying that this P has components of viscous and pressure. I can also have components of gravity, which I will say it's acting in some direction like this. Okay, so therefore this is the gravity contribution. I am separating that from the viscous and pressure contributions. So I will write those contributions separately. So as far as the work done by the pressure for the pressure and the viscous forces are concerned, so it should be U dotted with P, and they are acting on the surfaces, so it should be integrated over the surface. So this is one contribution. The other is coming from the gravity, so that is U dotted with rho g, and this is a body force, right? This is acting on the entire volume, so this should be a volumetric integral. So what is the final contribution? So you have the work and energy, heat. Okay, so the heat will be Q dotted with the normal, and once again it is a surface integral, right? Now what should be the magnitude of this? Should it be what should be the sign of this, plus or minus? Okay, so in fact I should give it correct representation here. So in my thermodynamic definition, the heat transfer to a system is positive, therefore I will denote that my heat flux is actually entering this particular. So therefore Q dotted with N will be negative, so I have to put a negative sign here to make sure that this convention is the positive heat transfer. Alright, so according to this is opposite to the normal. Okay, so this is the positive definition of heat that is added to a system, and this has to be negative. So that's it. So once you have written this for this particular control volume, control mass, so okay, so this is for a control mass. Okay, this is the first law for closed system. All of you agree? There are no flux terms, so this is very straightforward to write than for an open system. Now you know directly the Reynolds transport theorem, which links the closed system to a control volume. So just replace the left hand side with the partial derivative terms, okay, and therefore you will finally have your conservation of energy for an open system. Okay, so if you do that, so I will just erase this. So this will, on the left hand side I am going to replace that with the Reynolds transport theorem formulation. I have V d by dt of this particular rho into u plus half u dot u, okay, the entire thing, okay, anyway, plus I have I can use the tensor notation rather than using the divergence notation here, d by dx k. So I am going to use this particular notation into rho u plus half u dotted with u, okay, multiplied by what, uk, okay, the entire term dv, okay. So I am replacing this control mass derivative with a control volume derivative, that should be equal to d by dx k, okay. So this should be just as it is, integral s u dot p ds plus integral u dot rho g dv minus integral q dot n ds, okay, where my p vector here is nothing but the viscous stresses, okay. So that is sigma ij into n vector, okay. So this is my compact notation for these viscous forces which are acting on this particular control volume. So is it clear? So only the left hand side I am writing in terms of the Reynolds transport theorem control volume derivatives. So now you can apply the Gauss divergence theorem, you can also express this and write this in terms of volume derivatives, okay. So therefore I can say my integral u dot p ds will become integral d by dx I uj sigma ij dv and integral q dot n ds will be integral over volume del qj by del xj into dv, okay. So you please understand the tensor notation here. So in this case you simply say dqx by dx plus dqy by dy plus dqz by dz, okay. Here this is a tensor, okay, sigma, this is a stress tensor, okay. You have all the 9 components, so you have to go one by one. So you start with say I equal to 1, j equal to 1, and then I equal to 1, j equal to 2, so and you keep expanding this, okay. So this is a very compact way of writing all those terms, okay. You can go back and check with your Cartesian coordinate system, okay, whether this makes sense, okay. So I am just going to write this in terms of volume derivatives. And therefore if I put them together I can say the integrand should be 0, because I can collect all the terms which have volume integral, okay, on the left hand side, and that will be equal to 0, and therefore the integrand has to be 0. Therefore the integrand becomes d by dt of my rho u plus half uj, so which is the compact notation again, plus d by dx k rho u plus half uj uk, okay. So now you see if you are going from k equal to 1, 2, 3, so you are adding all the spatial derivative terms with respect to x, y and z in Cartesian coordinate system, okay. And for each of this you are saying this is u square plus v square plus w square. So you have two notations here, one for j, one for k, they are independent, Okay, so this J will go within the K loop, alright. So then you have to expand that for the different coordinate systems K equal to 1, 2 and 3. So on the right hand side you have Uj, okay, so this should be d by dxi into Uj sigma ij plus Uj into rho Gj, this is the body force term, minus you have dqj by dxj, alright. So this is your energy equation. Now this has to be closed, and one more thing we can do is, this has all these complex terms which we can probably simplify. Once again we can write the mechanical energy equation in a tensorial form and we can subtract that from this, okay. So the mechanical energy equation, if you multiply your momentum equation by the velocity terms, okay, and sum all the three momentum equations, so your mechanical energy equation in the tensorial form can be written as d by dt rho uj by 2, okay. This is like rho u square plus v square plus w square by 2, okay, that is E, plus you have d by dxk rho uj by 2 uk. So what you are doing is you are multiplying with uj, so that is for x momentum you have multiplication with u, y momentum v and z momentum w, and this k is basically your spatial derivative, the divergence operator essentially. So you have u du by dx plus v du by dy, so that is taken care by this k, so that k is different from this j, okay. That is equal to uj d sigma ij by dxi plus rho uj vj. So for a particular momentum, x momentum, you will have gravity in the x direction, y direction and so on, okay. So this also is the stress tensor. J here indicates the direction along which that stress is acting. So in the x direction you will have sigma xx and tau ix and so on, and this is the, since it is a tensor, it has to be the gradient in that particular direction, okay. So for x direction you have d sigma xx by dx, the y direction you have d tau ix by dy and so on, okay. So that is the compact way of representing that, all those terms in the Cartesian system. So now if you subtract, let us call this as number, we already used number 1, no, okay, somewhere we used before I think, but let me redefine as number 1 and this as 2, and subtracting 2 from 1, so I will be left with an equation for only the internal energy, so subtracting 2 from 1, I can say that I will get an equation like d by dt rho u plus d by dxk. So these two terms get cancelled off, I will get another term here rho u uk. On the right hand side I will have sigma ij, because if you expand this, this is sigma ij into duj by dxi plus uj into d sigma ij by dxi. So uj into d sigma ij, and this when you subtract they are gone, okay. So you will have sigma ij into duj by what, dxi, and the body force term gets cancelled off directly, then you will have minus dqj by dxj, alright. So what I am going to do, I am writing this term in terms of total derivative again, which you know is du by dt, and you know for incompressible fluid, now I am going to bring in the relationship between the stress and strain rate. So I can say sigma ij equal to minus p. So I am going to write this in terms of the tensorial notation, and you will see that this is a very compact, you do not have to write this for each and every component, by dxj plus duj by dxi. Does it make sense where delta is your Kronecker delta? So delta ij will be equal to 1 if I equal to j equal to 0 if I is not equal to j, right. So what it means, only for your normal stresses you have minus p, the pressure forces come to balance the normal stresses, whereas the tangential stresses do not have the pressure force to balance that. So there they will disappear because this is your delta function. Okay, so wherever you have normal stresses, only there the pressure stresses will be there, otherwise it is 0, and this is a common representation. Okay, so this will be say du by dy. If you suppose you have I equal to 1, j equal to 1, then this will be du by dx plus du by dx, that is twice du by dx. Okay, if you are writing your tangential stresses, so I equal to say 1, j equal to 2, so this will be du by dy plus dv by dx, which are the components under shear stresses. Okay, so depending on the particular index I and j, this can be written for all the components, normal component or tangential components. It's a very compact notation. Okay, for those of you who have probably not known, any of you not heard of tensorial notation? Okay, so I think you may have to brush through any basic fluid mechanics book. Maybe usually in the appendix there is something on tensorial notation, or you can just quickly read through tensors. It is, I mean, it is very common sense, you can see that from yourself. You do not have to expand that, you can substitute. If it is 2 dimension, I and j can maximum go to 2, if it is 3 dimension, so you can just expand it in that manner. And if you represent something like this, that means this is a summation operation. You do not just stop like this, you have to expand it, okay, for different values of j and I, that is what it means. Okay, so therefore now if I substitute this, you see how easy it reduces to the final form in the tensorial notation. So this gives me rho du by dt. Okay, so this will be, I am substituting for sigma ij in terms of this, so minus p into du k or duj by dxj plus d by dxj of, so I am also using the Fourier's heat conduction law for q, and I am writing this in terms of the temperature gradient dxj, okay, plus you will have some other terms which form the viscous dissipation right here. In fact this will be 0 by continuity, right. So what I am doing is I am clubbing all the pressure terms. So if you write this, this is p delta ij, and this will be 1 only if I equal to j. Therefore if your j and I are equal only, that term will be there, and when they are equal, that is nothing but the continuity equation for incompressible flow. Okay, so that will automatically be satisfied. Therefore you will have your total derivative, that is equal to your Laplacian operator right here plus your viscous dissipation term, and for incompressible flows, so this phi what I have written here, you can see that for yourself will be nu dui by dxj plus duj by dxi times what? Fill in the blanks. What will be the multiplication factor here? So I am just substituting this into this particular term. Okay, the pressure term I have cancelled it, duj by dxi, right. Okay, now you can go back and check for your Cartesian system whether you will get all those terms. You know, you can start with say du I equal to 1, j equal to 1, and you will get 2 du by dx into du by dx, so that will be 2 du by dx the whole square, 2 nu du by dx the whole square, and if you have plus, then you have to expand in y z direction, so you have other dv by dy plus dv by dy the whole square plus dw by dz the whole square plus, now if you go to I equal to 1, j equal to 2, then you will get your other terms du by dy plus dv by dx. Now this again has to be expanded for different values of j, so again if you do that, you will get dv by dx plus du by dy the whole square, okay, which you have derived in the Cartesian coordinate system. So this is a very compact notation, alright. So now therefore that is your final energy equation, which you have you can write down in a coordinate free representation, okay, for a control volume. So this is finally for a control volume. Okay, so therefore I think this gives you a pretty good idea how the Reynolds analogy can be applied to derive the conservation equation. So all the Reynolds analogy says is you can transform your variation with respect to a control mass to a control volume, okay, and you have to write down the conservation laws for a control mass, which is much simpler, and then you apply that relationship and then you write the final equation for a control volume, okay, and this is a completely coordinate free representation. So any questions? So what you have to do is go home and then check once whether all these tensor notations make sense to you, and if you have any questions you can ask me, okay. So it takes some time for you to understand this completely, but it's not that difficult either, okay. So working with tensors, you don't make any mistake, so that is another advantage, and finally it's up to you to expand that in whatever coordinate system that you are working, okay. So very quickly what I am going to do is another 5 minutes I am going to go over to the second law of thermodynamics, because we have derived all our required conservation equations applying the first law for energy, but we have to see something about more important fact, which is entropy generation, okay. When you have heat transfer, you have some kind of entropy generation inside the system as well, so the heat transfer results in some internal irreversibility, and we will see how this internal irreversibility can be characterized, okay, very briefly, okay. I am not going to go into too much of detail. Okay, so I am just talking about the second law aspects now. Okay, so I am talking about irreversibilities and entropy generation, and you all know we can start with the Clausius inequality, which relates your change in entropy to the amount of heat transferred. What it says, if you have a perfectly reversible process, so your ds is equal to this is your perfectly reversible process, okay. If you had differential amount of heat, so you can relate your change in entropy directly with this particular relationship, okay. You can calculate the change in entropy if you integrate this particular equation, okay. Now if you have some internal irreversibility, what it says is your ds is greater than or equal to this, so usually for internal it should be greater than this, so we can also say, or otherwise ds is equal to this plus some entropy which is generated inside the system due to irreversibilities. These irreversibilities could be, one of them could be from the viscous dissipation, okay. In the energy equation you have a contribution of viscous dissipation, right. So what it says, even if you do not transfer heat, that viscous dissipation is sufficient to increase the energy of the system. That means part of the kinetic energy is converted into energy, into internal energy of the system, okay. So that can cause additional irreversibilities. Apart from that, your conduction or heat diffusion itself will generate some internal irreversibilities, okay. So we will Now try to estimate, okay, what is the contribution of the heat transfer and your viscous dissipation to the generation of heat entropy. Okay, that is a very important thing, because it is not just enough to understand the conservation law, we should also understand and characterize what is the contribution of these components to your entropy generation in a system. Okay, therefore we will just quickly expand this for a closed system. We can write this in a rate form as ds by dt is greater than or equal to 1 by t dq by dt. Okay, this is nothing but the heat transfer rate. Okay, so you can call this as q dot or whatever, heat transfer rate. So for an open system, okay, so what I am going to do is I will express this total derivative. This is for a closed system. I can use the Reynolds transport theorem, which I have, expand the total derivative in terms of the partial derivatives. I can say that this is my total entropy. Now if I define an entropy per unit volume as a property, so I can write this as rho into S. So this is the entropy per unit mass here, I am sorry. Okay, this is your entropy, specific entropy. So therefore the alpha, which is entropy per unit volume, will be rho times S and integrated over the entire volume plus what is the second term. Okay, so this is your S into so this is rho S times, so this will be the velocity component, okay, which will make your derivative here v dot n ds. This is integrated over the control surface. This should be greater than or equal to, if you integrate this again over the control surface, because your heat transferred is transferred across the control volume boundaries, okay, dq by dt, okay, ds. Alright, so this is your equation for conservation of entropy. So this is an entropy conservation equation, you can say. For an open system. Alright, so it is just like your energy conservation. You can write something in terms of entropy flux, okay, and your rate of change of entropy with respect to time, and that should be greater than or equal to your heat transfer which is happening divided by time, the temperature, sorry. So what we will do now is that we will expand this particular term on the right hand side, okay. So we will apply Gauss divergence theorem for this term as well as this right hand side term, and we can expand that term a little bit, okay. So if you write in terms of the Gauss divergence theorem, so what I am going to do is that so this difference, ideally if you do not have any internal irreversibilities, this left hand side minus the right hand side term should be 0, right. If that is greater than 0, that means you have some internal irreversibility. So what I am going to say, your internal irreversibility S dot gen is equal to this minus this, okay. So which is nothing but your rho ds by dt, okay. So I am just writing this in terms of the total derivative, plus I am going to expand this particular term. I will write that using Gauss divergence theorem as del dot 1 by t, this can be written as del dot 1 by t del q by dt for the entire control volume. Alright, so this can be expressed as 1 by t, I can write this as del dot q double prime. Now the del q by del t is nothing but the heat flux primarily. So this can be written as del dot q, I can take 1 by t out, minus I can take 1 by t square q double prime dot del t, okay. I am just splitting this derivative, I am just expanding, I am just saying this is 1 by t, if I take out this is del dot q double prime minus, if I take q double prime out, so this is 1 by t square q double prime dot del t. I am just expanding and rewriting this. So this is my final expression, which says that my generation term has something like a total derivative plus this plus this. So if you ideally balance all these terms together, you can calculate your irreversibilities internally. Okay, so we will stop here, and tomorrow we will continue and show what are the final expressions for the contribution to internal irreversibilities.